Modern vector databases represent a paradigm shift in how data is stored, searched, and retrieved in the digital age. At the intersection of big data and artificial intelligence, vector databases have emerged as a powerful tool for handling complex, unstructured data types like images, videos, text, and audio. This video delves into the mechanics of modern vector databases, elucidates their advantages over traditional and other No-SQL databases, and explores their growing relevance in today's data-driven landscape. Understanding vector databases. To appreciate the innovation behind vector databases, it's essential to first understand what vectors are in the context of data. Vectors are mathematical representations of data in a high-dimensional space. In simpler terms, they're arrays of numbers that encode the features of data points, whether those are words in a document, pixels in an image, or timbral characteristics in an audio file. This encoding allows for the nuanced comparison and retrieval of data based on the distance between these vectors in the multidimensional space. With various distance metrics, for example, cosine similarity, Euclidean distance, used to quantify similarity. Vector databases are designed to efficiently store, manage, and retrieve these vector representations. They leverage advanced indexing algorithms and machine learning models to facilitate fast and accurate searches across millions or even billions of vectors. The core technology enabling these databases to perform similarity searches at scale is often referred to as approximate nearest neighbor search algorithms. These algorithms are optimized to quickly find the vectors closest to a query vector within high-dimensional spaces, striking a balance between accuracy and computational efficiency. How modern vector databases work. The operational foundation of a vector database is a marvel of modern computing, meticulously engineered to harness the vast potential of high-dimensional data. This process is predicated on three pivotal stages: vectorization, indexing, and searching, each of which plays a crucial role in the database's ability to process and retrieve information with unprecedented efficiency and accuracy. Vectorization, the first step towards understanding data. Vectorization is the transformative process that converts raw data into a format that vector databases can understand and manipulate vectors. This conversion is not merely a change in format, but an elevation of the data into a higher dimensional space where its essence is captured in a dense numerical form. For textual data, algorithms such as Word2Vec, BERT, or GPT come into play, analyzing the semantics and syntactic structures to produce embeddings that encapsulate the underlying meaning of words, sentences, or entire documents. In the realm of visual content, convolutional neural networks scrutinize images, distilling their complex patterns and textures into feature vectors that represent the image's core attributes. This process is equally applicable to audio, video, and other unstructured data types, each undergoing a bespoke vectorization process tailored to its unique characteristics. Indexing, organizing data for swift retrieval. Following vectorization, the resultant vectors are methodically organized through indexing. This stage is critical for enabling efficient retrieval from the vast expanse of vectorized data. Modern vector databases deploy a variety of sophisticated indexing structures designed to navigate the complexities of high-dimensional spaces. Tree-based structures like KD trees and ball trees offer hierarchical organization, allowing for partitioning of the space in a way that facilitates efficient search operations. Hashing-based methods, such as locality-sensitive hashing, transform vector space into hash tables where vectors are bucketed in a manner that preserves similarity, thus optimizing search efficiency. Graph-based approaches create networks of vectors, where edges represent similarity, enabling dynamic exploration of the closest neighbors through graph traversal algorithms. The choice of indexing method is pivotal, directly impacting the balance between search speed and accuracy. Advanced vector databases may employ a combination of these indexing strategies, dynamically selecting the most appropriate method based on the query's nature and the dataset's characteristic. Searching, the quest for similarity. The culmination of the vectorization and indexing processes is the ability to perform similarity searches. When a query vector is submitted to the database, it embarks on a quest to find its nearest neighbors within the multidimensional space. This search is powered by approximate nearest neighbor algorithms, which are engineered to quickly sift through millions or billions of vectors to identify those most similar to the query. These algorithms, through a judicious trade-off between precision and computational efficiency, ensure that the search process is both fast and accurate. The resulting vectors are then ranked by their degree of similarity to the query vector, providing the user or application with a list of the most relevant data points. The search process in a vector database is not just about finding exact matches, but uncovering patterns, relationships, and similarities that traditional databases could easily overlook. This capability allows vector databases to excel in applications ranging from recommendation systems and search engines to anomaly detection and beyond, where understanding the nuance and context of data is paramount. Beyond the basics, optimization and customization. To further enhance performance, modern vector databases incorporate various optimization techniques. These may include dimensionality reduction to simplify vector space, thereby speeding up search operations without significantly compromising accuracy. Machine learning models can also be fine-tuned to generate more discriminative embeddings that better capture the nuances of the data. Customization options allow users to tailor the database behavior to specific use cases. For instance, the choice of distance metrics such as cosine similarity, Euclidean distance, can be optimized based on the type of data and the desired notion of similarity. Furthermore, scalability considerations are paramount in vector database architecture, with distributed systems ensuring that the database can grow alongside the expanding dataset, maintaining high performance and availability. Advantages over other databases. Vector databases stand out for their unique advantages over traditional relational databases and other No-SQL databases, especially in handling unstructured data and executing complex search queries. Their architecture is specifically designed to address the challenges of unstructured data, enabling them to excel in areas where relational databases and conventional No-SQL solutions may falter. Efficiency in handling unstructured data. Vector databases offer sophisticated similarity search capabilities. By understanding the semantic context and subtleties within the data, they deliver highly accurate and contextually relevant results. Scalability. The scalable nature of vector databases is another significant advantage. Designed to expand horizontally, they can seamlessly manage the increasing influx of data supporting billions of vectors without compromising performance. The scalability ensures that vector databases can sustain the growth of data over time, maintaining high availability and system resilience even under the strain of massive datasets. Speed. One of the most compelling benefits of vector databases is their speed. Utilizing approximate nearest neighbor search algorithms and highly efficient indexing techniques, these databases can execute searches within milliseconds, even when dealing with extensive collections of vectors. This rapid retrieval capability is indispensable for applications that demand real-time search and analysis, enabling instant access to information in a way that transforms user experiences and decision-making process. Flexibility and adaptability. Vector databases are not just fast and scalable, they're also highly adaptable, capable of accommodating various data types and complex query requirements. This flexibility makes them suitable for a wide range of applications, from personalized recommendation systems and AI-driven content discovery to sophisticated analytics and pattern detection in large datasets. Enhanced data insights. By leveraging the depth of analysis possible with vector representations, these databases unlock new levels of insight into data. They facilitate a deeper understanding of content relationships, patterns, and trends, empowering businesses and researchers to extract meaningful intelligence from their data. Use cases and applications. Vector databases, with their advanced capabilities for handling and analyzing high-dimensional data, have found widespread application across several key industries and sectors. Their ability to efficiently manage and search through vast amounts of unstructured data has revolutionized how businesses and organizations leverage information for competitive advantage. Expanding the horizon of search engines. In the realm of search engines, vector databases have been instrumental in transcending the limitations of traditional keyword-based searches. By analyzing the semantic meaning embedded within the content, these databases enable search engines to offer results that are contextually relevant, even when the query terms do not match exactly. This approach enhances user experience by delivering more nuanced and tailored search outcomes, which are particularly beneficial in academic research, legal document retrieval, and niche information searches where precision and relevance are paramount. Revolutionizing recommendation systems. Recommendation systems, particularly for e-commerce and streaming platforms, have been significantly improved through the use of vector databases. By understanding the subtle nuances of user preferences and behavior patterns, these systems can offer personalized recommendations that go beyond superficial matching. For instance, in e-commerce, vector databases help in suggesting products that not only match previous purchase patterns but also align with the user's browsing behavior and product interactions, thereby increasing conversion rates and customer satisfaction. Enhancing content discovery platforms. Content discovery platforms, such as news aggregators and social media feeds, rely heavily on vector databases to curate and recommend content that aligns with the user's interests and past engagement. This capability is crucial in today's information-saturated environment, where the ability to surface relevant and engaging content can determine the success of these platforms. Vector databases enable a dynamic assessment of content similarity, ensuring that users are exposed to articles, videos, and other media that resonate with their preferences and behavioral history. Strengthening fraud detection mechanisms. In the financial sector, fraud detection systems have been markedly enhanced by integrating vector databases. These systems can analyze vast datasets of transaction patterns and customer behaviors to identify outliers or anomalies that may indicate fraudulent activity. By comparing transactions in a multidimensional space, vector databases can detect subtle patterns of fraud that would be missed by traditional rule-based systems. This not only helps in minimizing financial losses, but also aids in enhancing the security and trustworthiness of financial services. Personalizing healthcare services. Healthcare providers are increasingly turning to vector databases to personalize patient care and improve diagnostic accuracy. By analyzing patient records, medical imagery, and genetic information as vectors, healthcare professionals can identify patterns and correlations that inform treatment plans and predict health outcomes. This application of vector databases is particularly promising in the field of personalized medicine, where treatments can be tailored to the individual characteristics of each patient. Challenges and considerations. Despite their numerous advantages, the implementation and operation of vector databases present certain challenges. The complexity of machine learning algorithms and the need for specialized knowledge in high-dimensional mathematics can pose barriers to entry for many organizations. Additionally, as vector databases often handle sensitive and personal information, ensuring the privacy and security of this data is of utmost importance. Compliance with data protection regulations, such as GDPR in Europe, requires robust encryption and access control measures to be in place. Moreover, the computational resources required for maintaining and querying vector databases, especially at scale, can be significant. Organizations must carefully plan their infrastructure to balance performance needs with cost constraints. The dynamic nature of data also necessitates continuous tuning and updating of the machine learning models used for vectorization to ensure that the database accurately reflects the evolving characteristics of the data it stores. Conclusion. Modern vector databases represent a transformative leap in data management, blending cutting-edge algorithms and machine learning to redefine data analysis. These databases excel in handling unstructured data, providing superior search functionalities and scaling effectively to accommodate the exponential growth of big data. They are setting new standards, outperforming traditional databases with their ability to conduct nuanced similarity searches and manage vast datasets efficiently. The integration of advanced machine learning techniques, such as deep learning, has further refined search precision, while explorations into quantum computing promise to exponentially increase search speeds. Future developments hint at an even closer integration with AI, expanding the potential of vector databases into critical areas such as healthcare, predictive analysis, and cybersecurity for advanced threat detection. As we move forward, vector databases are poised to become more integral to our digital existence, offering robust, scalable solutions that convert complex data into valuable insights. They stand at the forefront of a data-centric future, promising to unlock the untapped potential of unstructured data across diverse sectors. With each technological advancement, vector databases continue to evolve, promising a horizon where data's depth and complexity are fully realized and utilized. That concludes this episode. If you liked what you saw, leave us a like and subscribe to our channel. hit the notification bell so that you don't miss out on any updates. Thank you for watching.